Okay, good morning. So for the midterm results, okay, I discussed with TA. The TA said basically the midterm grading is done. They just need a little time to input everything into Compass. So likely we're going to release your scores by Friday, okay, tomorrow, because they need a little time to check, verify, and then finally input the scores. So for discussion for the midterm, maybe we can do it on Tuesday or so, but anyway, you already know the scores. We're going to distribute your exams back on Tuesday, okay, but not today. Okay. So don't worry about it, but I probably say you just check on Friday because the TA already promised me they're going to release it on Friday. Okay. So then for the new assignment, I just say, I saw a lot of discussions in PS already. You really should try it early, okay, especially for those who has not studied yet, not started yet, okay. So the due date is, I think it's November 2nd or so, November 3rd. But, for programming assignment, you always want to start early because you may encounter some problem. Okay. So that's about the assignment. Okay. One thing I should remind everyone is last time we discussed about midterm, final exam. Okay. If you really cannot make final exam on this date, December 15th, okay, you should send me formally by written form, means you should send me email earlier, okay. Claim what exactly time you would prefer, because we cannot do it late. We can only do it earlier, okay. So you should let me know, because we will need some time to discuss and finalize the date on the alternate exam. Okay. So hopefully, you plan it earlier. You know what is exactly time. So we will announce it, at a proper time. Okay. So we are going to continue our discussion on our I think, this seems to be a little different from my previous slides on my screen, and also it's here. Probably I should do it alternatively. Not sure what is the problem. Okay. No, it's a little different. Let's see, they probably use. The previous one was using something different. Let me try to make sure this is okay, but if I put it here, is there any way I can make it bigger? Display settings. Duplicate window and the slideshow. Yeah, now it works. Okay. Yeah, so last time we discussed about sequential pattern mining. Okay. Sequential pattern mining, we introduced a few algorithms. Finally, we say our own algorithm, prefix span, probably is the most interesting, most efficient one. Okay. The general philosophy for prefix span is pretty straightforward. You got a sequence. You first find frequent one, that means single one is frequent. Okay. Then based on this frequent one item set, for example, if you find A, B, C to F are frequent, okay, you get an A's projected database, and you get a B's project database and C's project database. You base on the projected database. And for each projected database, you find its frequent one element, okay, one item. Okay. For example, you find A is also frequent, you predict on AA. If you find F is frequent, you predict on A after F. Okay, then you predict anything after F. Okay, like this one. If it's predicted on F, this part is empty, this is empty. This F, you will get a CB. This F, you will get a CBC, right? So you based on this, you generate lots of projected database. For each projected database, you mine the same way. Then you can get all those sequential patterns mined. Okay. And we also said to make things more efficient, you don't have to do physical projection every time. If your projection is minorly different from the previous one, you actually can project it just by pseudo projection. That means you just adjust your pointer. Say, oh, now the string is here. You know, for this particular string, you adjust the pointer, you know, after this particular one, like AB. You adjust pointer to this blue, to this green one. Okay, so then you are done. So it's a pretty straightforward algorithm, and it's pretty easy to implement as well. And we also show this is far more efficient than many other algorithms because you avoid any, you know, combinatorial, you know, like generate a large number of candidate sets. So this essentially candidate set you generate one at a time. And we also said if you really find some sequence, they got a frequent altogether. Okay, it's very frequent, it's closed. You want to directly mine these closed patterns. Like last time I said, if you find lots of people, they first buy iPhone 3, then buy iPhone 4, buy iPhone 6 and 7, you know, doing this kind of thing, then you get a one larger, longer one. You avoid to generate all the sequences, which, you know, just a fragment sequence. Like you can say iPhone 3 then 4. You can say 3 then 5, 3 then 6, 3 then 7. Okay, then you get a 4 then 5. Then you start get a size 3, size 4. That doesn't make too much sense. You just get a longer pattern. It definitely will make a lot of sense. Then we will have very similar definition on the closed sequential pattern. Okay. So we say, what is a closed sequential pattern? That means you find this sequence S, which is frequent, and there's no super pattern S prime. The super pattern just a, you know, a superset of your sequence S. And these two have the same support. That's exactly the same definition almost as your frequent pattern, except now order is important. Sequence. Okay, it's a sequence. So then you can easily, after a midterm, I think you can easily work on this one. I say, which ones are closed? Is this ABC20 is closed or not? No. Why it's not closed? Exactly. Okay. You can see, you can find a longer one. It has exactly the same support. That means actually you need to generate ABCD directly rather than thinking about to get ABC. Right? This is more like if you buy iPhone 3, 4, 5, so you don't think 3, 4 is close because you get the same number of people get 3, 4, 5. So you just show the longer one. Okay. So that's why ABCD is closed. What about ABCDE? Why ABCD is closed, ABCDE is also closed? Because they have different support. You want to show both patterns. Okay. That's why if I say max pattern, if I say support is 10, anything over 10 is max pattern, you will generate ABCDE. But if I say closed pattern, that means the difference of the support does count. That means both ABCD 20 and the ABCDE 15, both are, closed pattern. You need to mine it. Okay. So that's a difference. If in a final exam I give you this, you will say, oh, this is a piece of cake. It's so easy, right? But remember, you struggled a little in the past, right? So now the interesting thing becomes this. Okay. Why we want to directly mine close sequential path? Obviously, directly mine is beneficial because what about you get an iPhone like 3, 4, 5? The other one said, okay, this is 3, 4, 5, 6, 7, all closed. Okay, you directly mine this rather than look at all the combinations. Definitely, it's more efficient. Right? So that means we can reduce those redundant patterns to be generated, and you have the same expressive power. That means you show the longest one implies the shorter one is also 20. So why bother to show all these so many times, right? But it's not that easy to mine close to one, actually. There's one interesting property. Actually, that's what I told you, this Xifeng Yan. Actually, this is his second year PhD. He came here 2002. Okay. The second year, he already got quite a few very good papers. Okay. This one actually was, he found this property, then developed a very interesting algorithm. Okay. The property actually saying this. Suppose you got a sequence, say A, F. In the meantime, you also generate projector 1, F. That means AF as a sequence is frequent. F is also frequent. Okay. 1 is the other one's superset. You can say AF is F superset. But how do you judge, whether you don't need to mine F anymore because this one is AF is you just mine AF. Suppose you generate F. Okay. You would say, oh, I don't mind the remaining one because actually this F is just a subset my AF. They are, if I keep mining this part, I'll get exactly the same thing as my AF. Okay. It's more like you think about it. You get an iPhone 3, get an iPhone 4, and get an iPhone 5. Sometimes you may say, I don't mind iPhone 3 because I only mine this iPhone 5, the remaining part, I get all the same thing. Why I have to mine each one? Okay. So how do you judge it? Okay. He found it's something very easy to judge. You don't have to look at the whole database. You try to judge them. Okay. Look at every projected sequence you try to judge, to try to make a good judgment. What he made a very easy judgment is if these projected database have the same size, that means the same number of sequence. That means if this one you find is 3,000, you find this one is also 3,000. Okay, 3,000 sequence remaining because they project from the same large sequence database. Once you say AF, you project it, you get 3,000, and you project on F, you also get 3,000. And he says, because you project from same parent, you get same size, actually, you can judge they are closed. Okay. Closed means this AF and F, you mine this F, you get anything, actually it's a subset of this. Okay. It's just absorbed by this. Then there's no point. You try to mine this part because this part is the same as the other one. You get it closed. So can you prove this? Actually, if you think about it, if they are really closed, if this one got the same size, you finally find the pattern you get is the same, this one gets the same, you actually can easily see this one and this one, they have the same number of transactions, okay, same number of sequences. But if they have same number of sequences, because they project from same parents, you also can say the finer you mine them, you get the same thing. They are close. Okay. So he spent a lot of time actually to prove this, and he first just writing the program, try to find one. He found this property. Then he finally proved it. Okay. It take a little thinking to prove it. It's in the paper. But then he developed a very easy pruning method. That means while you mine it, you find anything, you can prune the remaining one because you just want to mine closed one. Okay. What he got is he has a backward sub-pattern pruning and a forward, a backward super pattern pruning. what is backward subpattern, what is backward superpattern is, of course, you mine this part. You first project on A, then project on F, you find this part. Then later, you just found F is also frequent, you project on F. You can see this F is this one's subpart. It's a substring, subsequence. And then you find they have the same size. That means their project database, you have the same size. Then at this point, you just do not do this anymore. You just put a pointer here. You say AF and F, you finally mine, you get the same thing. So you do not need to mine this F's project data. So this one is a subpattern. This part is superpattern. You can see this part is B, this part is EB. Okay, this is superpattern. But this superpattern actually is also, part of this. You also just need to mine one instead of mine both. Okay. So he basically found that you can have these two ways to clone the remaining project database. That means you don't even have to mine this project database. If you find, this part have the same size as is either subpattern or superpattern. Like this one is a subpattern. I mean, this B is this one subpattern, and this AF is this F superpattern. Right? So he derived a very efficient algorithm. Still find all the, close patterns, but you don't have you short circuit many mining things you don't have to do. Okay. The result is also more compact. So that one becomes a method called close span. Okay. If you go to the web, actually he put open source on the web. Of course, we put a prefix span as well. And then this close span, most people are using it. Most people actually use, they call prefix span algorithm. Actually, what they use are the close span, because you only mine the close pattern, which is shorter. Okay. I think you still, even now, you go to our Illumine or go to Professor Xifeng Yan's website, you will find this open source algorithm you can use. So it's a very good algorithm, very efficient. Okay. Now we get another issue is constraints. That means even mine sequences, people want to put constraints. For example, suppose you got a sequence of transactions for different customers. So you may want to see, you say, sum of this one is greater than 150 or less than 150. You can put this sequence. You can put a minimum of this value is greater than 10. All kinds of things you want to put. Remember, even you study, for example, Amazon. Suppose you go to Amazon.com, this company. You want to find different customers, valued customers, or customer want to buy this kind of thing, do not want to buy the other things. You study the whole sequence of the customer shopping, right? Once you get a sequence, you may put a different constraints. Then your mining will become more interesting because that's exactly the things you like to see, right? So they have exactly almost the same thing. You probably can see almost the same kind of properties we work out. This is another paper by Yan Pei. Okay, he actually, after he worked out the prefix span, he worked on the constraints one as well. Okay, and there's anti-monotone. Anti-monotone means, okay, once this one violates this constraints, you put more things in the string, in the sequence, it still violates. So like this one. Like if you say the sequence, this people, you want to find this customer, okay, total of the price they bought is less than $150. But if you find this customer so far got more than $150, you add more, it's still over $150. So just don't search this customer anymore, right? This frequent sequence anymore. Because you want the sum is less than 150. Okay. The same thing like this monotonic says, if you want, the customer shopping sequence contain PC and digital camera. Okay. So the monotonic means once you find this sequence contain these two things, you don't have to check this constraint anymore. because it's always, you add more things in, it always contains 2 items. Right? The data any monotone means if you want this one to be greater than, say, $100, but you find if this whole customer, this shopping sequence is less than $100, $150, so you don't have to even add this one in because this customer were not contributing to something you want to find, to the patterns you want to find. If you want to find pattern, say sum is over $150. This customer only shopping for $30 for the whole sequence. Why you have to even look at this? Right? So you can sort this. So this is anti-monotone. Right? And succinct means, for example, if you say you want to find the customer, the shopping history contain iPhone and Mac Air. Okay? And what you need to do, because these 2 are so explicit, you just try to find those customers, they buy iPhone and buy Mac Air or something like this. Then you start with this, right? Because those are the customers that will only be hopeful to satisfy this constraint. Okay? Same thing as convertible. Convertible is a little trickier because remember for the item sets, those transactions, you can swap the order. You can say, I make it price ascending or price descending. You can easily do that. But shopping sequence, you just cannot change the sequence. Right? I can first buy expensive item, then I buy a cheap one, I buy another expensive one. How could you shuffle it? It's not the sequence, you just cannot shuffle. Right? So then Jen actually found, even you cannot shuffle. If I do projection, I always can say, I first project the most expensive item, then project the second most expensive item. The only difference is now I do not say I only look at their postfix, their suffix. I don't look at suffix. Why I project this, I know the front one is still useful. Okay? So when I projected this, I actually keep the front one as well, if I haven't done it yet. Right? So that's the only difference. And you still can use this, say, average value less than $25 or greater than $25. You still can use this. Just to change the rule a little. Originally you do projections, only look at the suffix. Now, because I projected not in the exact shopping sequence order, I hold this expensive item, the front one still counts. Because I project not start one by one in this order. I project the most expensive one. I put it down. But the front one, I still want to use it. Right? So I still keep the front one. You can see that it's just to change the prefix span algorithm a little. You can handle this. Right? Of course, there will be a homework or exercise you can play with it. So this is constraint-based mining. And there are more constraints if you think about a sequential pattern. Sequential pattern, because you have the sequence, you can give it more constraints. One called order constraints. Order constraints means I give you the order, something must happen before something. Okay, just thinking about it, if I say, if you want to take CS512, you have to first take CS412. Then it become a constraint, become a sequence. Here I give you, say, if you want to learn calculus, you have to first learn algebra and geometry, or something like this. Okay. That means you first learn this, you can learn calculus. Otherwise, you will not be able to understand the course. Okay. In that sense, you may have an order. Then, with this order, you mine the sequential database. You say, anything follow my constraint order, I will get it. Anything does not follow the constraint order, it goes somewhere else. Right? So that's order constraints, which is anti-monotonic as well. Right? Because you violate the order, subpattern violate the order, you will not be able to get a super pattern. You just can prune the whole thing. Right? And you can have min gap and max gap constraints. For example, you can say, I can look at the people first by iPhone and by Mac Air, but in the middle, it must be the minimum gap is say 5 or something, or maximum gap is 10 or something. You always can give this. For example, you can even give the time constraints. You say, it must be within 60 days. I want to find this pattern. That means buy iPhone and buy Mac Air is within 60 days. Okay. Why you want to find this? Because you may want to give the coupon or give some advertisement to those customers. They are very active shoppers, right? So that means you can give a max span constraints. The max span constraints, for example, you say maximum span is 60 days. Then when you do the mining, because you do not know which customer buy the first item. For example, which customer first buy iPhone. Okay. But once he or she got this iPhone, you will start counting the time. Okay. Then see whether this guy will buy Mac Air within 60 days. So that means the constraints, you will enforce it once you find the first item is in your box, in your target. Okay. Then you start counting time, 60 days. Right? So you will see whether this guy will buy the otherwise or not. So we call this one max span constraints. And you also may have window size constraints. For example, you have so many shopping things ongoing. You may say, I take the window size, one thing can be window size is 2. I look at the 2 transactions. I was thinking they are almost like same. Like if you buy things within 1 day, you will think almost the same transaction instead of a sequence or something like this. So you can play with this based on your application. Okay? If you go to Walmart, go to Amazon, you can set up all different kinds of constraints, find customers with different characteristics. So this is still pretty useful. People can see this constraint-based mining we learned in transaction mining. Now get a sequence mining. You can expand it. Okay, you can. That means many things we learned here is still useful because those anti-monotonicity, monotonicity. You can add more things in, and it's very easy to add more, right, based on your application. And there's another kind of pattern which is not exactly a sequential pattern. And people call this is episodes. Okay, they call it episode mining. What is episode? You can think the sequential pattern is serial episodes. You mean say first come A, then come B. That's sequence. But you also may say, I want to find a parallel sequence. Parallel episodes. Time is important, but I want to find these things happening in parallel. Okay, so then that becomes parallel episodes. And then you can have regular expression to express the episodes. That means you may want to find a pattern like this. A, B happen together, okay, in parallel or approximately parallel, and then get a C, this pattern multiple times. You can see C, get a star. Star means 0 or more times, right? You can have C happen 5 times or happen 0 times. You can have this. And then you say D happen, then E happen. Okay. You may write down pattern like this. That means you can give me regular expression like this. Remember this A, B, C, D, E are all the real items. Now it's like X, Y, Z. You can replace this with any real pattern. For example, you can say, I found this guy buy iPhone and iPad at the same time, and then after that he will get like a Mac Air. Then he will get another thing, right? So you probably can find this pattern. You go down to the shopping sequence. You say, I want to find this kind of regular expression with minimum support something. You are going to find it. So this they call episode pattern mining. That means you can write any regular expression and push it in. In principle, the mining algorithm should be able to find this efficiently. That means once you know item sets mining, sequence mining, you can easily generate this one into episodes mining. Any regular expression you put in, and they can give you out. The algorithm will be somewhat similar to sequential pattern. So we are not going to give you the general algorithm. I just say you can do generalization of a priori algorithm or GSP algorithm. You can get this. Okay. Or you can do project-based pattern mining. That means you can do projection. There's no I haven't found any paper doing this, projection-based binding. So I just put it down here, say, can you work out the detail? If you work out the detail is the same as prefix span, I probably say this is the nice homework. But if you work out even more efficient algorithm, you can send it to a conference, publish it. You invented this algorithm. Okay, we haven't seen serious study on this, but somebody in the class can invent new algorithm and get it published. Okay. So actually, in the CS 512, almost every year we got some students invent new algorithm, publish in a very good conference. Some even get an award. Okay. So that's the one you can see. There are lots of things can be studied along the line, and they are very rare. That means you go to companies, they really like that because you really can find a lot of things. Okay. Especially you work for like a Walmart or any store like Amazon, right? Now we study the last one in our pattern mining is graph pattern mining. What is graph pattern? Okay. I do not know anybody study chemistry, but I think at least you in the high school you learn something about it. Organic chemistry, right? You know, the organic chemistry give you very fancy, nice pictures. Those are the structures, okay? Right, like some other, like a band ring, okay? Some organic chemistry, you get carbon, oxygen, hydrogen, and nitrogen. They all link together in some very fancy way. Okay? But those fancy ways are very important. Okay? For example, I remember one day I went down to see a chemist, biochemist, downstairs in the life science building. I said we can mine some free patent for like those kind of patents. I said whether you are it's useful or not. He says, I'm working on those antibiotics. Antibiotics like a penicillin or all these antibiotics. And antibiotics is so important because remember the early days of the 20th century. Anytime you get a flu or you get some kind of minor thing like some germs, basically it's threatening your life. You could be killed even in the childhood. Okay. But once people invented antibiotics, okay, there are lots of originally very serious problems like TB. Okay. Basically, in the past, it's more like a death sentence. But once you get antibiotics, you can cure it easily because those are the germs. Those antibiotics can cure it. Of course, now why he's still studying it is that there are serious problems. Probably you know it. It's they call super germs. What is super germ? Superbug is the antibiotics human did not use it properly. Okay. Then they use, for example, you got some problem. You just the doctor said you have to take this medication for 1 week. They take 1 day or 2 days. You say, oh, I'm recovered. I don't need to take the remaining one. Okay. Then you think you are okay. But remember, there are some germs you are not completely cured them. They survived. Okay. Then they developed some resistance to your antibiotics. Now the resistance is so huge. Okay. That means even human developing many antibiotics, there are some bugs. They are resistant to all the human developed antibiotics. They still survived. Then, if you got this kind of superbug, you're unlucky. They can kill you easily. Okay, you see, there are reports of these antibiotics, resistance problem cured in the world every year now is in the order of millions. Millions of younger people like children or very old people like elder people or even in the middle age. Okay, you could get it cured because we have no antibiotics to save it, to cure those bugs. So what he says is it's important. Why? To find new antibiotics, you have to know those structures. He actually told me, I think this Professor Mitkoff, okay, he actually told me, he says, I work on antibiotics. There are hundreds of antibiotics. There are chemical structures. I can write on the whiteboard every one. I remember it in my mind so clearly. every chemical structure of these antibiotics, I know it. I can write it. But what's important thing is they want to develop new ones. They want to change those structures, develop new ones. Those bugs did not see it. They don't have the resistance. You still can cure those bugs. Okay, so that's his task. It's very important. Right? You can save millions of people now. Then it becomes interesting is we want to mine patterns of these graphs. Okay. What is patterns? That means something happens very frequent in some drugs or some chemical. Okay. If you want to find that they are completely the same, you got the complete same drug. You do not have new things. What you want to find is they have some subparts are the same. Okay. What is subparts are the same? For example, if you look at these three things, okay, A, B, C are three chemical compounds. Then you may find that something is frequent. Maybe if you said minimum support is 2, you may find some substructures are the same. For example, if you see here, you have 2 nitrogen, you have this kind of bond, then you have an oxygen. You may find this one, this B and C, they all contain this part. Of course, you want to find a larger part. If you say everything contains carbon or carbon linked with carbon, this is everything, right? So you won't find anything not containing this. But if you find a bigger structure like this, you say, oh, these 2 antibiotics contain this structure. Those cannot cure germ, does not have this structure. Maybe you play with this structure, you may develop new drugs. So that's, of course, nowadays, most antibiotics were developed not by computers. Okay? They go down to those dirt, those kind of some kind of a thing in the nature. Okay? Go to some forest, get some dirt. They try to find some germs there. They twist it, you may find a new antibiotic. That's most antibiotic research is doing that. But they do analyze their chemical compound structure to see the structure is similar to the previous one, but it's different. They may have some power to cure germs. The germ does not recognize it. So that's what they are doing. Okay. So my previous student, Shifeng Yang, he actually, after he did this whole span, those things, he jumped into this graph pattern. He actually, when he first came to my office, I remember clearly, he just said, I just want to find good research topics. What are the research topics? I first give him this topic, graph pattern mining, subgraph pattern mining. He's a very smart student. He first asked me, what's the use of it? Okay. I could not find a very good use. I just say, you can see we mine the transactions, we mine the sequences. Those are all data structures, right? You get a sequence and transaction. Then you get the most complicated structure is a graph. So we need to mine subgraphs. I sort of giving some web. He was not convinced that this is a very good application. He was working on computer vision when he was doing master. He went back. He said, if you don't convince me, this is worth study. There are many applications. I won't take it. Okay. But then later, after a week, he came back. He said, oh, I found even in computer vision, you want to find the cars. The car has a structure, right? You get a body, you get a wheel, you get something. That's actually the substructure. If you go down to the street, you get a video camera. You find many, many such substructures. These are the cars. Okay, I found this substructure actually is useful. And then he found this chemical compound is more useful because you find those very complicated, very big subpatterns, subgraphs. Okay. So then he got very excited. He said, I have to develop a new algorithm to mine this. Okay. So what is frequent subgraph? The frequent subgraph basically says you have many, many graphs. You can think everything is a chemical compound or is a picture, is a say your digital camera picture, like here. Okay. Then what you want to find is some kind of a subgraph, substructure like this. Okay. Then you have minimum support means you give me 1,000 pictures. I may say 10 is a minimum support. You have to find those things, common structures, like buildings, cars, person, or dog. Okay, you may find these substructures. You find those substructures if your support of this pattern, this substructure, is comparing to the total number of graphs of your transaction, your data. If it's greater than some minimum support, then this one is frequent subgraph. Okay. Then if you look at a chemical compound, you can see, if you set a minimum support is 2, you have 3 compounds. Okay. Then you will find this one support is 2, or this one support is 2 as well. But then you immediately you can see this. Actually, this one is a sub-pattern of this, because anything containing this one is part of it, right? So then you may say you still want to find a close one, the maximum one, because a big graph, the potential subgraphs, it contains is exponential. Right? You can think about any 1 is a pattern, any 2 is a pattern, any 3 is a pattern. It's exponential, right? You get an n, you get it 2 to the power n. Okay. So now we will see applications. You can see in bioinformatics, you may have gene networks, protein interactions, metabolic pathways. There are many things. Chemical, you will find many chemical compound structures. Social networks, you may have the sub-network structures. Cell phone networks, web graphs, XML structures. Even in software engineering, you may want to find a program substructures. Actually, I do have one student, he did a very interesting study, is try to find a plagiarism of the code. Okay. Remember, if you get a code, you copy this guy's code. Okay. Then you can change all the identifiers. Okay. You change while loop to for loop. You can change many things. You know they're identical. You can copy this and put it into your system. You say, I never copied this guy code. Actually, you copied it exactly, but you do not copy the whole thing. You only copy the essential part. And you can, some statement you can swap it. Okay. So I do have a student. He actually got similar to this graph pattern mining. He finds these structures, and he finds essential structures. He then those non-essential, you can swap them. Okay. And essential structure, if it's a loop, you can change it for into while into repeat, whatever you like. It still can maintain the same graph structure. Okay. Then he just say, if you maintain exactly the same graph structure with some swapping, actually these two are identical. Okay. These two algorithms or two software code are identical. He can find a plagiarism even. And he did have a one called GPLAG. It's a graph-based plagiarism. Okay. It's a very interesting way. Many people ask him about the code. Okay. So this is software engineering. There are many things you need a graph. A graph definitely is very useful. Okay. Now we go down to graph pattern mining. Actually, before or after this Xifeng Yan's work, there are several different methodologies on mining graph patterns. Okay. One is using apory. Actually, before Xifeng Yan got into this problem, tried to work on it, actually there were several groups. One was in Japan, in University of Tokyo. Another was in Minnesota, University of Minnesota. There are already two groups working on graph pattern. But what we worked on is using apory. Okay. That means that the same thing you find is size 1, then you find size 2, you find size 3. The same way as apory, but you work on graphs. Okay. So this apory-based algorithm. And Xifeng actually like our pattern growth algorithm, because you can see the pattern growth as a very nice feature. But the problem is graph has no starting and ending point. You can grow almost anywhere. It's very hard to control because you have an exponential number of ways to grow it. Okay? It's hard to tame. Okay? So, but he said, I will try to work on this, work out a pattern growth algorithm and compete with the a priori-based algorithm to see which one is more efficient. And he developed a very efficient algorithm. Okay. The algorithm called G-span, because he first worked on this closed span. We have a prefix span, closed span, and he just wanted to use the same name. He just say G means graph, so to get a G-span, it's graph span. Okay. And they are search order, breadth first and depth first. If you think a priori algorithm, essentially breadth first, because you find all the size 1, then you go all the size 2, then you go all the size 3. So it is breadth first search. The depth first search is you grab this one and say, which one goes with me? Okay, you get one more edge. Which one goes with me? You get one more edge. So this actually is the depth first search. Okay. So there are lots of very interesting algorithms on different ways. Let's just first get into the concrete one. Okay. The concrete one, the first one is a priori-based approach. What is a priori-based approach? Essentially the same as item sets mining, but now you work on the graphs. Okay. What on graphs, how do you work it on is this. You have lots of small graphs. You can think in this, everything is a chemical compound. Okay? You get thousands of chemical compounds, you want to find frequent subgraphs. How do you do it? You first try to find a frequent one, which is just an edge or just a node. Okay? Actually, there are two kinds of methodology. If I show you the next one, I think that this one actually shows there are two ways to do it. One is you grow one edge at a time. Another is you grow one node at a time. Okay? But we just say either edge or node. You basically grow one component at a time. Okay? Suppose now you start with one edge, you get into two edges, into three edges. Now you get a k edges. Okay? So how do you get a k plus 1? Okay. So that's exactly the same thinking as a priori. What you do is this. You take this k-edge graphs, all of them. This is a breadth first search. You get all the k-edge graphs you already found, frequent ones, over your minimum support, the frequent ones. And how do you get a k plus 1 edge? Remember we said the a priori means you think about item sets. You get milk and butter. Now you get cheese. Okay. How do you think milk, butter, cheese? These three will be frequent. You get this candidate is you say you must in the size 2 you can find milk and cheese, okay, milk and butter, cheese and butter. You get all these things. Then finally you will be able to find these candidates 3. Okay. That's the same idea. What you do is this. You try to get one candidate with size k plus 1. There will be k plus 1 smaller k-edge graphs. They are almost the same except they have one edge different. Right? You think about it. You must contain this k plus 1 k-edge graphs. They share all the k minus 1 edge, except one edge is different. Now you say, now I try to combine them, I'll get a k plus 1. If you cannot find such k plus 1, this kind of subgraphs, you will never be able to get a k plus 1 edge because of the apple. Right? Because anything getting this to be frequent, their subsets must be frequent. If you think about this chemical compound, you can think in this way. If you want to find this one is frequent, actually, you may chop this edge, say this one must be frequent. You may chop this edge, say this must be frequent. Chop this one, say that one must be frequent. Otherwise, there's no way that you can get this one's frequent, right? So you can see you have many, many k plus 1, these kind of common things. Then you will get a candidate. Okay? So that's the a priori algorithm in the graph context. Okay. This algorithm was developed by University of Minnesota. Actually, it's also the first author is a Japanese called Hamaruchi. You can see. This is Kuramochi. This is the Minnesota. George Karipis is a professor. This is the PhD student. Okay. What they developed one is FSG, or fast subgraph. Okay, FSG. Okay. Then before that, even 1 year before that, a group of Japanese researchers in University of Tokyo, they read, Rakesh Agarwal's 1994 paper on APRI. They work on the graphs. They developed this one called AGM, APRI-based graph mining. Okay. They developed this AGM algorithm. Okay. The AGM algorithm is generating one vertex at a time. That means they don't look at the whole edge. They look at a vertex. They add a vertex, they then add edge. They go a little slower. Okay. Then Kuramochi and Karipis, what they got is they adding one edge at a time. Okay. So that's a difference. But they show their ICDM 2001 paper showed their algorithm is better or more efficient than AGM because they add bigger components. And that component is a little rarer than adding edge. Okay. So to that extent, if you look at this, what you can see is their idea is, suppose you get this as a carbon ring. Of course, in reality, most of the carbon ring is 6 carbon getting together. It's a benzene ring, right? Ben ring. So you probably can see this is a carbon, this is carbon. And suppose you get one element is D or E, okay? So for this, you will be able to generate quite a few candidates. You can say DE may be this way, or because remember this carbon, this C, any C is a carbon. They do not stick on this node. You may generate a pattern like this. You may generate a pattern like this, because remember the carbon, you can turn the carbon, anyway. You will generate different patterns. You can generate lots of patterns. Okay. And of course, you have to check the candidates. So that means basically based on the performance, you can see the edge growing is better than the vertex growing. Okay. They basically show the edge growing, the FSD is more efficient. Now we come down to pattern growth approach. This is Xifeng Yan, his approach. Okay. And he published this paper actually even earlier than his closed band algorithm, because I first asked him to work on graph pattern. He first worked out this algorithm. This is the first ever paper he have ever wrote. Okay. And he wrote in a very theoretical way, but not a very good explanation. The interesting story was this. Okay. The reviewer read the paper thinking there's some interesting stuff, but they do not understand what's going on, right? So everybody said, oh, I'm sort of neutral, but I tend to accept it, but they say it's really complicated. So they finally, the review score was not so high. They accept as a short paper. It's a very short paper. It's only 4 or 5 pages. But anyway, a very short paper. But I have another student, Huan Jiu. He almost finished PhD at that time. He wrote a nice paper, accepted as a full paper. Those papers got accepted. It was in Japan. It's so far away, and there are visa things. Both of them did not go. I went down there. I went to Japan to present. And they saw the same group. They arranged in the same session. One is long, one is short. Okay. I did a swapping. I say, this long paper, it's a nice paper, but I present it, you can quickly forget it. Okay. But this short paper, I will use a long paper time. I'll present a long one, you will never forget, because this paper will be very high impact paper. That's the reviewer just could not understand it. Okay. They were laughing. They were thinking I'm biased. But it happened. This paper, after 10 years, they found this paper is in their whole proceeding. This is the highest side paper. It's a short paper, but it got 170 1,700 citations, even that time, 10 years. Then they give this paper the 10 years highest impact paper award. So this, and even when I think, say, John Kleinberg, who actually in the KDD conference, he's the guru of the web. You probably know the web has two major algorithms. One is the Google's algorithm is called rank, page rank. Okay. The other one is his algorithm, hits. He got the innovation award for KDD. Even in his innovation award, he presented those things, cited a few papers. One paper is this paper. That means even for the highest genius in the web, on the web, he still liked this paper. Shifen was sitting beside me. He says, you give a very good advice and work on this problem. This is the first paper I ever wrote. I even thought, whether it can get accepted or not. And then finally became the most famous paper in the whole graph pattern mining. Okay. So what he did actually is pretty interesting. It's not easy, actually, the paper. What he was thinking is this. I got a K edge. If I can say anything containing this K edge, go with me, only those graphs go with me. I start growing. I say there are several ways to grow. I grow from the K to K plus 1. I grow this K edge, K plus 1 edge graph. Then I just say any remaining graphs in my graph database. You contain this K plus 1 edge, go with me, then I can keep going. Okay, that's the same thing as our FP growth. Okay. But the problem, the major problem is the graph, actually the structure, can turn around. You probably know the graph isomorphism test is NP-hard problem. If you work on any complexity, they first take the graph. The graph is most complicated. Anything you touch, you get NP-hard. Okay. So what he did was very smart. Okay. You think about it, what he did is this. He did it is he wants to say even the graph has so many ways to grow. Let you think about it. You get a carbon, you can turn around. The carbon you can turn many different ways to get the same graph, right? But he says all these graphs, if I want to find a frequent pattern, if I give all these same nodes an expansion order, so you only go this way, okay? I still find all the frequent graphs. Then I avoid the combinatorial problem, expansion problem. Okay. So what he did is this. He says, for any graph, if I want to find a frequent pattern, I assign some kind of expansion order on this graph. Okay. For example, you find this kind of structure. But I assign expansion, so you expand, follow one order. This is more like a frequent pattern. Remember the frequent pattern we say? We assign the frequent order, the most frequent one in the front, the second most, the third most. Actually, somebody, even in the midterm, in the previous midterm, point out one problem is I actually give this order. There's one order which is not strictly follow the frequency descending order. Like, remember I give you the different nodes. Some actually is out of order. Actually, out of order doesn't matter if you really do your algorithm. But there's one order. The remaining expansion must follow this order. Whatever order you have, the remaining expansion must follow this order. You can use descending order. You can use ascending order. You can use price ascending order, or whatever alphabetic order, whatever order you need. But you need to give me one fixed order. All the expansion follow this order, you get all the patterns. Okay. So basically, this is a similar kind of idea. What he said is, if we follow rightmost path extension order, okay, rightmost means this. Okay, if you go this graph, you can say this is if I start from here. Rightmost means the first one goes here, the second one goes here, the third one goes here. Then you can see if you use rightmost, these three, can only go back here. Okay, if you want to expand it, you only go back here, and this 2 you can go here. So that means if you follow, you see, there are several ways to go. Every time I have 2 roads to take the right one. Of course, you can take the left one. If you take the right one, all the expansion must take the right one. Okay. Then, if you have a similar graph structures, I will find their similarity. That essentially is saying, originally graph you turn around with so many different ways, you have so many ways to grow. He basically say, if everybody follow one way to grow, you still find all the patterns. But you don't find these combinatorial explosion patterns. Okay? So that's the trick. And he proved you follow any particular order, like rightmost path expansion order, is still complete. That means you do not miss any pattern. You still find a complete pattern. Just everybody follow this. You don't find a repeated, this turnaround pattern, but you still find the same structure, same graphs. Okay. So that actually means he actually can turn this graph into depth first search code. That means he turned the graph in using this depth first search, turn the graph into a sequence. That means originally graph was so complicated, so combinatorial, so many ways to turn around. Once he set up an order, he essentially turned the graph pattern mining into sequential pattern mining graph. And then he can use his closed span to do anything. Okay. So that one actually becomes a very, very good problem. And he used this one, develop an algorithm. I did not show the concrete one, but essentially is once you know how to turn a graph into a sequence, basically solve the problem. Okay. Then another important thing is you want to find a closed one. Okay. Because like I just give you said, the small one, any combinatorial small one is still frequent. You get so many. You want to find the largest one. Okay. So that means, like here, suppose you get this big graph. Okay. This big graph, maybe, actually he is very interesting. He went down to the big website on the NCBI, as National Biological Information, some website. They have lots of graph structures about genes and chemicals. He went down there. He actually mined a lot of very interesting graphs, like for AIDS or those kind of virus, what kind of substructures they have or something like that. I mean, the drugs which can cure AIDS, okay, those drugs. There are many drugs. So you want to find, common substructures. So the closed one, the definition is the same. Okay, you can see. You say a frequent graph G is closed if there exists no supergraph of G that carries the same support as G. That's exactly the same closed pattern. Now it's closed graph pattern. Right? You have closed sequence, closed item sets. Now it's closed graphs. Okay. And closed graph is lossless compression. That means you actually find everything, but you just show the largest one. The smallest will come in the combinatorial thing, you don't show it. Okay. So that's the closed pattern. And he actually tried to find a closed graph pattern. He actually worked out an algorithm on finding a closed graph pattern. That means after his G-span, he actually worked out this closed graph. What is closed graph? The general philosophy is you start mining K edges, you get lots of these ones. The closed one essentially is saying some part of the expansion, like growing this, because one part you grow, the other part if you grow, maybe you get the same thing. You get the same support, same kind of structures. You need to terminate some growing. That's exactly the same as our previous thing I will show you here. You can see this one. This is his closed span. The closed span basically say you have to test this one and this one one is essentially the same as the other one. You don't mind the second one. You only mind the first one. Now it is a graph. It is more difficult than this because the sequence, you know where it starts, where it ends. The graph is turning around. You actually do not know what's the remaining part of where you want to start, where you want to end. So that's actually is more sensitive. Okay. Even you show the order, but there are some substructures maybe embedded in different ways. Okay. So he actually spent a lot of time trying to work out to make sure his termination is right. That means you don't mind the remaining, for example, some of this growth maybe contain the graph which is completely subsumed by the other one. You get same support, same number of support, same kind of structure. Then some later one you don't have to grow. You just grow this one, you know it's complete. Okay. But trying to find this termination condition is very tricky because the graph can grow in many different ways. They actually share the same structures. Okay. Sometimes you may miss it. Okay. That means that you may still waste your time to grow something which is already close. Okay. He spent lots of time trying to cut out anything which he guaranteed you can terminate. Okay. So if you read this closed graph, the general philosophy is clear. The remaining ones are how to cut this. You guarantee this part, actually you expand, you get the same thing. Okay, so then you can cut it. I'm going to show you, actually, he really mined a very interesting one. And he actually went to NCI-NIH website. Okay. He found there are lots of compound. Is AIDS antivirus string compound. What does this mean? You probably know AIDS in 1990s, when the people just got this AIDS, they basically death penalty within a year or so. You will die very miserable. Okay. But later, in late 1990s, people found some drugs. Actually, it's not a one drug, but it's a group of drugs. And you have to take it almost every day periodically. Okay. Then they can control the HIV virus without exploding, without really getting full exploding AIDS. So you can live almost in the normal lifetime span. Okay, so that's we call a cocktail, some kind of treatment. Of course, this for U.S. maybe it's okay because the drug is very expensive. You have to take it every day. But you still go to those developing countries, they cannot afford those drugs, they still die. Okay. But then he found those drugs. He tried to mine those drugs to find a common compound structure to see whether there's a large substructure may have lots of them. Okay. He went down there. He found that the data contained 43,000 chemical compounds. Of course, there's lots of research on it. And he mined this pattern. He found if you set minimum support as 20, you may find this structure. But you lower down support, the structure you find is bigger and bigger. Of course, you lower down support means less number of chemicals contain this structure. So you can find a bigger structure. And he found like you get 5% support, you can find this big structure. And the mining is very efficient. He actually showed, like, remember this runtime is exponential. Exponential means you go one part, you get 10 times more time to mine. And he shows this FSG. They're using Apple-based algorithm. Is here. That's Minnesota's algorithm. It's here. Okay. Then his algorithm got here. But if you only mine a closed one, you can drop 10 times more efficient. You get this. The number of patterns you also drop quite a lot because you only mine a very large one. The small one, they have the same support. You don't show it. So the number of patterns drop by order of magnitude. The mining time also dropped by order of magnitude. Okay. If you read this curve, you'll find it's a little strange because it seems the running time is going down. Actually, you should read in reverse because this is you set the support higher, you get less results because you say 10% is frequent, then you get this rate. If you lower down and say 1% is frequent, you get much more things jump out. Right? You can see. This is 10% frequent. This is 5% frequent. From the 10% drop down to 5%, your running time jump order of magnitude higher because you lower down support, you get more bigger pattern mine, right? Because you only require a small number of compounds contain this stuff. You get more things mined. So that's the reason you can see. For any frequent pattern mining, you see the curve like this. Actually, this is the higher support. This is lower support. Lower support is much more challenging because more things will come out. Will come much more patterns out. And in many cases, you may want to find lower patterns because you want to find those bigger structures. Okay, so we finish all the pattern mining. Okay, you probably see that it's a pretty long one. The interesting thing is the pattern mining is still quite useful. If you do the homework, you will find the pattern mining is very useful for finding phrases. Right? Actually, I did not put this one into the lecture, but if you go to CS512, you will find it's very interesting. For example, okay, we got one student, we got two students, one already graduated now in Google Research. Okay, he just joined Google Research in 2016. I have another student currently still here. What they mine is this. They go down to mine the phrase structures, like United States of America is one phrase, right? You say U.S. President or U.S. President Barack Obama, it could be one phrase. You find those phrases, and of course, human can recognize it because you read the newspaper all the time. But the machine automatically finding those phrases, actually it's not that easy. Okay? And especially if it's in different languages. And they use this frequent pattern. Of course, it's a little more than this pattern. But they found, for example, you go down to Wikipedia or go down to some different languages. They actually mine the frequent phrases in many, many languages. Actually, at least now, people told me almost all the European languages, you can mine a phrase in a very high quality. And he also tried Chinese. Chinese is much more difficult because there's no gap between the words. Okay. I mean, if you think about English, you write anything, there's no space. It will become very hard to read. And that's the nature of the Chinese language. So, and try to find the phrases is much more challenging. And he found it was very high quality phrase. But based on frequent pattern. So this is a very useful thing. And it's still coming. We still have some very interesting papers coming out. But interesting thing is for frequent pattern, this campus, what we did is really, really leading in the world. Okay, you can see there are many, many algorithms coming here, and people use it widely internationally. That's also for Coursera. Like Stanford, they got this Coursera. They first say for data mining, we have to do pattern mining, pattern discovery, in this campus to give the first Coursera on data mining. And it's interesting. Last year we got this one. This is all the papers. We got this pattern mining one. The first time get this pattern mining, we got 80,000 students registered internationally from 140 countries and from many, many different language studying groups. Actually, there are many, many different languages people studying this pattern mining in the same course. So this one is anybody knows where it is? Little Mermaid, right. This one actually is in Copenhagen. Okay. You probably know Hans Christian Andersen. He wrote many, many very, very good stories, very good ones, like Cinderella. I mean, this Little Mermaid is one of his work. And he is Danish. Okay. His major creative place is in Copenhagen. So this one is their city symbol. You go down to Copenhagen, everybody say you have to go down to the ocean to see the Little Mermaid is here. So the proof of Copenhagen. Okay. So there's some additional reading, but I do not lecture you. If you like, you can read it, but it's not required. Okay, thank you.